So welcome back. So today we're going to talk about the details of programming in the shared memory model, which we've talked about before. So just to put this in context, I told you that there's a whole stack of different ways to think about parallel computing. There's thinking about the applications and how you take those apart into algorithms, and the last couple of lectures are about that. And then below that comes the software tools that you actually use to express the parallelism. That's what today is about. And in the past, we've also talked about the hardware layers. So today, in this stack of ideas from applications down to hardware, we're somewhere in the middle. So how do you write these programs? And so this particular set of models is good for shared memory machines. That means the multi-core processor in your laptop, or a single node of Hopper, the machine at NERSC, which might have 24 shared memory nodes on cores on one node. And so for bigger distributed machines, which is all the thousands of nodes on Hopper, we'll use a different programming model that we'll talk about next time. So that's going to be the first two-thirds of the lecture. And then the last third is I'm going to go back up to the algorithm level a little bit and talk about certain algorithms for which there are built-in functions in these programming models because they're so common, and I have to tell you why those algorithms are useful. So, let's get on to the first two-thirds. So I'm going to talk about two particular models. The first one is parallel programming with threads. That's sort of the most low-level way you could do it. It's very portable. It's based on a standard, on an operating system standard. And being that it's low level, it's kind of tedious to program in it. And so I'm going to spend most of my time on another shared memory model called OpenMP. And this is the one that is to be recommended to use in the shared memory programming environment. There's a international standards committee that's gotten together over the years, and they keep updating it. Most of my examples are going to be in the C language, but it's available in C++ and Fortran as well. And I'm not going to try to get into the details of exactly where to put all the semicolons. I'm going to give you sort of the high-level ideas about how to express parallelism in it. But there's an enormous number of other resources on the web, and here are some examples. That includes tutorials, video tutorials, manuals, as much detail as you like to actually help you write programs. And of course, for the first homework assignment, for the second homework assignment where you'll be using this, we're going to be handing you some code that you'll be modifying, so you won't be starting entirely from scratch. So there are other shared memory models. I mean, there's a lot of innovation in this area going on. So, for example, SILK stands for a language of the C ilk, and it was developed by Charles Leiserson at MIT and recently acquired by Intel. So it's another variation on this stuff. Thread building blocks, TBB, is another Intel variation on these packages. And so there are many ways to do it. OpenMP is sort of the most widely adopted standard. So after I present these different programming models, I'll take a simple benchmark and do a little comparison of performance, because all of these have different performance characteristics, and then I'll summarize. So let's get started with threads. So let me just remind you of the programming model that we're going to try, that these programming paradigms try to implement. And so it's shared memory. That means you should think of your program as a bunch of independent threads of control, a bunch of subroutines acting independently, if you like. And these can be created, when you start the program, or they can be created dynamically in the middle of execution. One subroutine can decide, I need, to split the work among 8 other subroutines, and it creates them on the fly. And so each such thread has a set of private variables. So when I loop from I equals 1 to n, only I can see I. Nobody else can touch it. But of course, these threads have to communicate, so they're also shared variables, which everybody can touch and see the same common value of. And so the way threads communicate is that they do it implicitly by reading and writing these shared variables. So here's a picture of such a machine. So down here is all the private memory. So processor 0 owns all that data, only it can see it. And so when processor 0 refers to variable I, it gets the value 2. When processor 1 refers to variable I, it gets its own value, which may be 5. So I is a private variable, and S is shared. So whenever processor 0 says Y equals S, it has to go to the shared space to get it. And when processor N writes it, S equals something, it changes that common variable. And so needless to say, you have to be careful to coordinate all these readings and writings and to do synchronization. So that's the model that that OpenMP and Pthreads are going to implement. And so, as I said, Pthreads is a Posix standard. Posix stands for Portable Operating System Interface. So it's sort of available anywhere that Unix runs. The IX gives you a hint that it's sort of based on Unix. So it's rather low level and portable, but it could be slow because it depends on the operating system to create threads and destroy them and so forth, and that's kind of a slow interface. So OpenMP is this standard application level programming. It's designed for scientific computing. You can put in a comment that says, please parallelize the following loop. So it tries to make it as easy as possible to express. And there's the standards committee. And as I mentioned, there are these two others. Java has had parallel threads built in it for a long time. It was motivated not so much by high-performance computing, but by having, for example, one thread which is watching to see if you touch a button on your laptop, and then it decides to do something, so it's meant for user interfaces. But parallelism is also implicitly expressed there. But I'm just going to concentrate on the first two. So here are the common notions of how parallelism is created by all these languages. So the simplest thing to begin with is co-begin and co-end. So and all the languages spell it slightly differently, but I'm going to use this sort of common notation. So in between co-begin and co-end, that says that every job inside that nest there can run in parallel. So job 1 is a subroutine that's called with input A1. It can run on one processor. You're telling the language it can run on one processor. And job 2 can run with input A2. And there's a scope here so that at the beginning of this, your program gets to this point. Here, these two jobs are spawned, and then you have to wait for them both to finish before you end. So when you get past this line of code, you know both those jobs have finished. So if job 1 finishes first, you may have to wait for job 2. And it's scoped so that you sort of can't, it would be a syntax error if I left out co-end. So that sort of prevents certain kinds of errors from occurring. So and this could be nested. So inside job 1, I could also have co-begins and co-ends. So I could have a tree of these processes that are created. So that's one way of doing it. The other way, that's a little bit more general, is called fork and join. And in that case, one process is running, and it says, I have some extra work to do. I'm going to fork another process to run. It's going to call subroutine job 1, and it's going to run on input A1, and I'm going to give it a name, because I'm going to need to ask later, is it done or something? Then I go do, on my process, I do job 2 on A2, and then I wait for this process that I started up there to be finished. So you can so now job 1 and job 2 are running in parallel, and this guy is waiting for the other process to finish. So here, this looks like it's doing about the same thing as this, but you can have much more kind of general patterns here that doesn't have to be nested in quite the same way. And there's also more room for little bugs that you can create by having this more general way of doing it. And here is another way of doing it. So you say, I want to call subroutine job 1 and input A1, and I'm going to use its output V sometime in the future. I don't need it right away. And so the job 1 goes off and starts executing somewhere. I mean, the compiler in the language worries about all this for you. And you go on and keep computing. So you execute a bunch of code, and finally, you need the output. You need the value V that you started computing on up here. At that point, it waits. If V is available, if job 1 has finished, you just keep computing, and otherwise it'll stop right there and wait until V is available for you. So this is yet another way people express this stuff. And so these are the two that are supported inside Pthreads and OpenMP. People are doing research on, is this a good way to write parallel code? This actually requires a little bit of hardware support to do it particularly well, and so this is something that architects and computer language people work on together. So anyway, so let's go back and talk about co-begin and forks and joins. So any questions about this so far? So these are shared constructs between both Pthreads and OpenMP. So now let me go and talk about Posix threads. And so it contains, as I said, it stands for Portable Operating System Interface, and the IX suggests it's for Unix. And it's very portable across all those systems. So it's going to have support for creating parallelism, the kind I just showed, for synchronizing, waiting for everybody to be done at the same time, more than just co-begin and co-end. And there's no explicit communication. Nobody sends messages because it's all shared memory. So if there's a shared variable that you have to, in the language, declare in such a way that makes it shared, and you refer to it, that's how processes communicate. So let's go look at the basic syntax for how you do this. So here's an example call of a subroutine in C to create a thread. And here's the signature, which sort of says what information you have to pass. So I'm going to call pthread create, and I have to tell it, I have to give it a name of what I'm creating so that I can ask later if it's done. Because I may call the same subroutine several times, I want to refer to those separate instances by separate names. I may give it some attributes. I may say, how much memory it needs to run, or I could just call null, and that would be, get the default parameters. Then I have to say what subroutine I want to call in parallel. That was the job 1, the job 2 on my previous slide. So this is the name of a subroutine you want to call and run in parallel. And this guy is the argument. So it's a pointer to some arguments that you pass to the subroutine and run in parallel. So here is the signature. So this is a particular type. It's called a pthread type. And then here I have a list of attributes. So what can attributes be? As I said, they could be the minimum stack size. You can have some jobs have higher priority than others. It's a hint to the scheduler which ones it should schedule first, or you can just leave it empty. This one is a pointer to a very general function. This is funny C syntax that says that this is a function which returns a pointer to an unknown type. It's going to take an argument, which is a pointer, and what's it going to point to? It's going to point to some function, right? So this is just C syntax and for how you pass in a function. And then there's the argument itself. Now, when you create such a function, it goes off and starts running. I mean, that's what you want to do. You want it to immediately go find another processor and start running. It may not work. I mean, what if you've created so many threads you've run out of resources? This call could fail. And in that case, when it comes back, it's going to return you an error code. If it returns 0, that means you successfully created a new job. You can go on and do what you want. But if it returns a 1, it says it didn't work. And you have to do something about that. So that's because that's a possible error feature. Okay, so let's do the simplest possible example of code. Hello world, it's a common application that everybody writes. And so here is the subroutine that I want to execute many, many times. It just prints hello world. And also it's going to print which routine is actually called it. So here's the main routine. I'm going to have 16 threads that I'm going to create. I want to call hello world 16 times. So I'm going to create an array so I can refer to each one of them. So I'm going to have one task, which is thread sub 1, another task, which is thread sub 2, thread sub 3. I'll have 16 of them, and they'll have those 16 names. And so now I have a loop from 0 to 15, and I create all 16 threads, and the first one is called thread sub 1, the next one is called thread sub 2. What is each one going to do? It's going to call this function, hello world, and not pass any arguments. So I won't pass any arguments to it. So now I've created all the threads. I've told 16 processes to go off and print hello world, and now I'm going to wait for them all to finish. So I have another loop from 0 to 15. I'm going to wait for all of the threads to finish. First I'll wait for thread 1, thread 0, thread 1, then thread 2, and join means wait until it's done. Okay, so this is a very simple little program. So let me give another example, which is loops, because a lot of scientific codes have loops, nested loops, and you have the parallelism there. So let me give an example of what that might look like. So here I have an array which has my stuff in it. There's some information in this n by n array. And I'd like to operate on each of those array entries in parallel and do something with it. And so here is sort of the most natural way you could do it. I could have two nested loops so that I iterate over all n squared possible entries of that array. And then inside that loop, I'm going to create a separate thread whose name is update cell sub ij. So there's going to be a separate thread for each ij entry. And I'm going to call some subroutine and pass in as an argument my stuff, that particular entry. So this would create n squared separate threads that would do something there. And that would be a perfectly natural way to do it. But would this be a good idea if all you did with this entry was, let's say, average with your nearest neighbors, do 4 multiplies and 4 adds? The overhead of creating this thread would totally overwhelm the 4 multiplies and 4 adds that you did. So even though this is correct, it would run, you'd spend all your time creating threads in the operating system and so forth. So you should do and if n is enormous, if it's 1,000 by 1,000 array and you create 1,000,000 threads, it's going to be overwhelmingly time spent doing that. Instead, if you only have 16 processors, you should only create 16 separate threads, and each of them will get 1/16 of the work. That would be a better way to do it. That's why programming in this particular Pthreads model, you have to sort of do all of that explicitly. OpenMP will make it easier. So here's some more Pthreads functions that you need to have in order to call to write the code. So you can tell the scheduler that I don't need very many more resources. Go ahead and give up my particular hardware process that you've allocated to me. I don't need any more resources. That's you probably wouldn't do that if you're each one is getting an equal amount of work, a subset of an array to work on. But it's available to you. The next one is when you're done, how do you say that I'm done with my thread and it's time to pass back my answer? Well, that's pthread exit. So then you're done with your thread, you sort of turn yourself off and you pass your answer back to whoever called you. Then if you're the thread who created this other one, you might need to wait for it to finish. In that case, you do a join. And this just sits there and waits until the thread whose name is this is finished and returns the result, which is that value there, and then you get it and you can keep on going. So another pretty common thing you need to do is if you create 16 threads and each of those threads is going to do 1/16 of the work, each thread has to know who am I, which 1/16 of the work do I do, so each thread gets an ID number. And so you can ask which one am I? Am I the first one, second one, third one by calling this function thread self, and once you know whether you're number 1, 2, or 3, you'll know which subset of the work to do. And so that's available to you. And then there's even lower level stuff which we probably aren't going to want to use where you can detach, and that says that nobody needs to wait for me. I promise that nobody cares whether I finish or not, and that's sort of a hint to the scheduler to do something special too, but chances are you won't want to do that. So let me give an example of how you use all this stuff to deal with race conditions, because we've had this situation before. So let's just go back and look at this example that we saw a couple of lectures ago. So I want to compute the sum of n numbers, and f of a sub 1, f of a sub 2, f of a sub 3, and I have two threads that are going to do that. And they want to accumulate the sum into this shared variable, s. So s is shared. And as I mentioned last time, if you just write it this way, you get a race condition because both of these threads are trying to grab the variable s and add to it at the same time. And if this guy grabs s and gets 0, and this guy grabs s and gets 0, and then adds it, s will miss getting the right sum. So the question is, what do you do in this Pthreads model in order to prevent that happening so that s is accessed the way you think it should be accessed? So here are the constructs that let you do that, different kinds of synchronization. And the simplest kind is called a barrier. And that's where all the processors have to agree to stop at the same point, wait for one another, and then continue. And so this is pretty common when you're running multiple copies of the same function in parallel. So if you have a big array and each process is getting one piece of that array to work on, and you want to wait until they're all done, you're going to be executing the same subroutine on a different subset of data. That's called the SPMD model. We've used that before, and then you want to all wait when they're done. That would be a barrier. So here's the way that might look. Everybody works on their subset of the information, and so let me use the two-dimensional grid example that we had before. So everybody wants to update some grid point, and it depends on their neighbors, and so everybody gets a square subset of the grid, and then for the grid entries that are in the middle, where their neighbors are on the same processor, you don't have to talk to anybody. That's what this does. Everybody updates the information that doesn't require any information from the neighbor, and then they all wait. They do a barrier, make sure they're all done. And then, at this point, all your neighbors have updated their ghost zones. They've all updated the stuff in the boundary. Then you can go read your neighbor's data and keep going. But you're going to wait until everybody's gotten the neighbor's data, and then you can continue. And so that's how you might write this code. So the barrier is a global synchronization. So you can do things that are slightly more complicated. You could imagine there's some algorithms where you have to break up, let's say, your grid into the even-numbered nodes and the odd-numbered nodes, or the reds and the blacks. There's all sorts of algorithms where you divide things in half. And so here's how you might write that. Every processor, as I said, can get an ID number. It knows what its thread ID is, its TID, ranging from 1 to P. And so this says if my thread ID modulo 2 is 0, that means if the thread number is even, I do something and then I wait. But otherwise, if I'm the odd-numbered one, I just wait until all the even ones are done. So you could imagine writing code this way in all sorts of different flavors. So barriers are not provided in every thread library, but they certainly are provided in Pthreads and OpenMP. So how do you do this in pthreads? You need to declare, there's a particular variable that's a barrier. You need to have a name for it because you can have more than one barrier, so you have to give it a name. And so you declare it to be a pthread barrier B, and then you can initialize it. And you can initialize it so that not everybody has to wait, because maybe you only want a subset of the processors to be working together and have to have a barrier. So you can say, I'm happy when 3 guys get there. That's enough. If 3 guys get to the barrier, I declare the barrier successful and I move on. So which 3 guys are you going to wait for? Well, you have the name. You just declared it. And so what you can do is give the name of that barrier to 3 processes. Then they will execute the barrier on that particular named one. And so those 3 can have their own common barrier. And so you can organize it any way you like. And so how do you actually spell wait at the barrier? You call a wait function, and you give it the name of the barrier that you're waiting for. So that's the most simple kind of synchronization. The next one I referred to before as a lock. So where you get to a lock statement and only one process is allowed to go past it, locks the door behind him, gets in this room, executes whatever it wants, and then leaves, and only one other process is allowed to come into the room. So there are different names for this, because historically it's been reinvented. So I called it locks. It's called mutexes, mutual exclusion, in this particular language. And so here's how you do it. You have to declare that you have a lock, and you can give it a name because you have multiple locks, so you have to give it a name. And you initialize it by calling allocate and init. And then when you want to acquire the lock, that means I'm going to try the door, see if it's locked, so you call acquire. Then you can do whatever and only one guy gets past that at a time. And then you can access the data, and then you unlock the door and leave, and it's the next one's turn. So it's acquire and release. So other languages, so this has been around for a while. So Java has it in there, as I said, because it was designed to have concurrent programming and program user interfaces. And they have lexical scoping. So this would be sort of a begin lock, end lock, and you couldn't have a syntax error by forgetting to unlock the door when you left and get a deadlock. So in some languages do that. And this also generalizes so that maybe it's the case that more than one process can access this data safely. Maybe it's set up so that there can be 2 processes in the locked room at a time, or 3 or 4. You can do that. The name and the people call this, or semaphores. You can decide that there are going to be k threads that are allowed in the room at the same time, because there's some shared resource and up to k can access it safely at the same time for whatever reason. So here's how you do the spelling in Posix threads. So you have to include this header file so that it knows all this stuff. And then you do a pthread mutex, that's the name of the type, and you initialize it, and there's the name of the lock, the name of the mutual exclusion. And to use it, you call lock and give the name of the lock, and then you call unlock. So that's how it's spelled in Posix. And so let's just see if this makes our life easy. So let's imagine we have 2 threads, and thread 1 unlocks and gets in the room called A, and then inside there you do another lock and you get in a room called B. And only if you get both locks can you continue. And thread 2 instead calls lock B first, and then it calls lock A. So is there a problem with this code? Yes, you can have a deadlock. So imagine if thread 1 does lock A and lock B and gets through, everything's fine, you can continue. But if thread 1 does lock A and thread 2 does lock B, then they're stuck, right? Because they're all waiting for the other one to give things up. And so it's easy to code deadlocks. Now, if your code looked like this, you could sort of see it immediately that this was a problem. But if this lock B, if this second lock is done in some subroutine, that comes later in the code, it may be very hard to recognize these kinds of deadlocks when they occur. And so indeed, there are a bunch of people doing research here and elsewhere on debugging tools to help automatically detect whether you've done these nasty things. And we'll have a little bit of a talk later on some of these debugging tools. But so you get lots of freedom to write bugs. Okay, so let me summarize. This is all I wanted to say about Posix threads before I go on to the easier version. So let me summarize. So it's all based on commonly available operating system features in Unix. They can be used from multiple languages. I showed you C, but you can do it from other languages too. And so most of the code looks just like your familiar C language sequential code, and occasionally you have to call these other subroutines. And the pitfalls are that it's very easy to create races and deadlocks and race conditions, and they may be very hard to find. And one of the things that makes debugging in this environment very hard is that bugs are often intermittent. You can run the program twice, and depending on how this gets scheduled, you may hit a deadlock and you may not. You may have a race, you may not. So it's not like you can run the program once and it works and you know it will always work. It could come up, the bug could occur in the second run or the third run, which is why people are trying to build tools to sort of help you prove that this could not go wrong. And so, as I mentioned, there's hardware support where people are trying to do transactional memory, so that when there's a shared variable, the hardware knows whether two processes are trying to write it at the same time, and it automatically warns you. That's not really available so much today. And then OpenMP is the common alternative, which I'll now go into. So are there any questions about Posix threads before I go into OpenMP, which is the one you'll most likely use, and you'll certainly use in the homework? Okay. So it's an open specification, which means there's this international standards committee that talks about it all the time for multiprocessing. And it's sort of the standard programmer interface for doing shared memory programming. There's the website for the international organization that's in charge, and they have lots of talks and free manuals and forums there. And as I said, we have all these other resources for how to program in it, and I'm not going to, again, tell you where all the semicolons go exactly. I'm just going to talk about how to express things at a high level. So most of what the interface looks like is comments. You insert comments into your code. They look like comments, but they're actually hints or directives for the compiler on what to do. So, for example, in front of a loop, you may say, comment, please parallelize this loop. And then it's the compiler's job to do it. So if you were to run your OpenMP code on a sequential program, it would just ignore the comments and it would run it in a completely correct sequential way. And so the nice thing about this is it works both sequentially and in parallel. So that's what most of it looks like. It looks like directives, hints to the compiler in the form of comments. There are some library functions to call to do certain things. And then there are also some environment variables where you can go say, how many processors are there? So you can figure out what to do. So as I said, it's a light syntax. You're mostly just adding comments to a sequential program. I'm going to show you examples in C, but it also works in Fortran and C++, so whatever language you like. So what you're going to do is break the program up into serial parts and parallel parts. You're going to have these hints that say do the next bunch of code, sequentially do the next bunch of code in parallel, rather than having to write a whole bunch of independent threads and coordinate them. It's going to hide for you automatically all the stack management, so that if you have a bunch of independent processes and they have some private variables, it'll do all that for you. And it will also give you some synchronization constructs. It still has to have barriers and so forth. But it won't parallelize anything automatically for you. You have to sort of specify all the parallelism still. There's no magic. It certainly won't guarantee speed up if you do a bad job. I mean, I already told you in Pthreads, if you spend all your time allocating threads that didn't do very much work, you'd be in trouble. The same thing could happen here. And there's no promise that you won't have data races. That would be too hard. So let me, again, do Hello World, which is the simplest possible program, and just talk about how to run it in parallel. So here's the sequential code. I call it once. And what I want to do is have a comment up here which says, do this in parallel. So here's what it looks like. So I'm calling a subroutine in OpenMP which says, set the number of threads to be 16. So I'm saying I want to have 16-way parallelism. And now I insert a comment which says pragma. This means it's a hint to the compiler. It's an OpenMP pragma, so I have to give that name because you could have some hints to some other processing system. But this is an OpenMP pragma that says, please parallelize this and use all the threads that are available. So this is going to call hello world 16 times. So the question is, what could possibly, let's suppose I set it up so that it printed out hello world 1, so that thread 1 would print out hello world 1, thread 2 would print out hello world 2. Let's suppose I did that. I haven't set it up that way. What could come out? So when you execute this, you have 16 outputs. Each one is hello world from 1, from hello world through 16. So just let's ask ourselves, what could appear on the screen? Are there any guarantees of what happens? So you could have hello world 1, hello world 2, but you could also have hello world 7, hello world 6. Could you have HHHE7, 16, LO, that kind of stuff? Well, it depends on who wrote printf. And when they originally implemented this, you could get that mess, right? You would have no guarantee of the interleaving of printf. Then folks realized you can't really debug, right? What else do they have for debugging other than printf? So printf is an atomic operation, and when printf starts, it sort of locks, prints out to the screen, then it unlocks so that the printf will work. So you won't get interleaved outputs. But that depends on the details of who wrote printf, and every implementation of OpenMP may do things slightly differently. I think they all get printf right, but there's the standard doesn't say everything that could happen. Okay. So the easiest thing to do is to parallelize loops. That's what OpenMP was for. And so the easiest thing to think about is a loop in which there are no dependencies. So that it doesn't matter what order you execute the loops in, you get the right answer. And so that means there's no different loop indices so that when I equals 1, it's reading something, and when I equals 2, it's writing it. Obviously, if you did those in a different order, you might get the wrong answer. Or if loop 7 and loop 8 are both writing the same location, again, you might get a different answer. So as long as that doesn't happen, you have to know that. Then it's okay to parallelize it, because when you parallelize it, it could happen in any order. OpenMP guarantees nothing about that. So here we have an equally simple program. I'm going to print out foo 25 times. And so here is sort of what the sequential program would do. It would loop I equals 0, print foo, test whether it's less than 25, and keep going around this loop. And so what is the OpenMP version of this going to look like? You just simply say OpenMP parallel for. So this is a hint to the OpenMP processor that this for loop should be done in parallel. There are 25 different things going on, and you're telling it, split up the work somehow among the available threads. And so, for example, if there were 4 threads, you would get these 4 things going at the same time. And you'd go around the loop, and it would take care of all of that without any guarantee of the order in which it's executed. So the question is, how does this pragma, how does OpenMP decide to take these 25 bits of work and do something with them? There's no one best way to do it. And so there's 3 choices that you can make, or you can just let OpenMP do whatever it wants. So, and so there are 3 choices because there's no one best way. The simplest thing to do is called static. In that case, it simply assumes all the iterations take an equal amount of time and divides them equally among processors. So if you have 25 iterations and 5 processors, each one will get 1/5 of the work, and it'll assume they'll all finish at the same time. And so that means that there's a chunk size that's allocated to each processor, and the chunk is simply divide the number of iterations by the number of threads and round up, and that's what happens. So that's the default that you get if there's no hint. But that's not always a good thing to do. It may be that some loop iterations take a lot longer than others, but you still want to have good load balance. So how do you deal with that? There's another hint that you could give to do it dynamically, and that says, please break up the work into chunks of some size. You have to say the chunk. And then what happens is whenever a process is not busy, it says, give me a chunk. I'll do it. And so everyone goes to this sort of common list of chunks and grabs one whenever it has work to do. And that sort of obviously guarantees some load balance, because if one chunk takes a lot longer than another, then that one processor will be busy for a long time, and the other one processes will grab work. Now, the trouble with this, of course, is that how do you pick the chunk size, right? So if you pick the chunk size to be really large, then you won't spend very much time going to this central list of chunks and grabbing stuff, so you'll have low overhead, but you may have terrible load balance. And if you make the chunk size 1, you might have really great load balance because everybody grabs one thing at a time, but you'll spend all your time going to the list and getting something to do. And the default actually is chunk size of 1. So the question is, how do you pick the chunk size? And so the last choice sort of has this clever idea, which is called guided scheduling. And the idea here is that at the beginning, you hand out big chunks, and then gradually, as you hand out more work, you give smaller and smaller chunks. So at the beginning, you get a big chunk of work to do, and so it doesn't take much time to go get it, and you're busy for a long time. But gradually, every time you get work, you get smaller and smaller chunks, so it'll probably balance out. Right? So it sort of tries to save time in allocation, save time handing out chunks by giving big chunks at the beginning, and then it tries to load balance at the end by giving out smaller chunks. And so the chunk size sort of shrinks exponentially every time it does an allocation. So it might hand you 100 loops, then 90 loops, then 80 loops, something like that. So this problem was addressed in this issue of how do you do this well. Oh, is there a question?
Yeah, so I was curious, what's the kind of big factor in terms of the overhead of handing out a chunk? Is it the communication? Is it deciding what to hand out?
If you do this in the when you implement this and there's one processor that has a list of all the chunks, that's a sequential bottleneck. Everybody is going to this one location to say, give me the next chunk, and if you have 1,000 processes lined up to go to that one location, you're in trouble. So that's why you want to have bigger chunks to hand out. So if you have a more clever OpenMP implementation, you probably don't have 1,000-way shared memory parallelism, so it kind of depends on how parallel you want to be. So there's yet another variation of this, which is not in OpenMP, but it's in Silk, which is this language of the C ilk. And what it does is it does work stealing. So in that case, if one processor so you hand out all the work, and if one processor is finished and doesn't have anything to do, it'll go look at some other process and try to steal work from them. It'll pick another random process and try to steal. So there's not like a centralized location where everybody has to go to it. And so there's a big design space on how people implement these things. There's no one best way. Okay, so let me now talk about the difference between shared and private data, because just as in Pthread, some variables you want to be private, some of them you want to be shared. The OpenMP and Pthreads do it differently. So I have to somehow distinguish between what everybody can see and what's private. And so here's how Pthreads did it. Let me just remind you. So if I declare a variable like big data is popular these days, and I do it at the top level in the main routine, that's automatically shared. And so if it's globally scoped, it's shared by everybody who's within that scope. But then inside this subroutine, which I could have many copies of running in parallel, if I declare something in there, it's private, just automatically. And so that might be my loop index. So that's how Pthreads does it. And OpenMP is different. You have to explicitly declare what's shared and what's private. So there's a declaration. You want to say big data is shared, and my local loop index, TID, or thread ID is private. And so that you have to have more explicit control over that. And then you do the calculation. Okay, so let's talk about synchronization. As I mentioned before, there's barriers and things like that. So how does OpenMP do it? So the construct they have here, which is analogous to a lock, it's called a critical section. Since this has been reinvented many times, people make up their own names for it. And so the idea about a critical section is that only one process is allowed to execute it at a time. So when all the processes get to this line of code that says this is a critical section, it's like having a lock. Only one is allowed pass to execute this code. Everybody else has to wait until they get there. So there are no explicit named locks. You just sort of say this is a critical section or not. You can have barriers, and they're spelled the same way. Whenever you get to this pragma OpenMP barrier, everybody waits until they get there. You can have explicit locks if you want. That's kind of a lower level thing. Critical sections are the easiest thing to do. You don't have to name it. But if you want to do this, it works. Now, the trouble is there's a problem with this, which is why it's not recommended unless you're a bit of more of an expert programmer. Suppose you declare a lock, and then you set it, and then you go in here, and then you unlock it. Where does this lock live? I mean, it's a variable. It's shared. But it may only live in your cache, right? There's no guarantee that it will live in shared memory, and that when somebody else accesses it, it depends on the hardware that they will get it. And so both of you, two different processes, could think they have the lock. And so there's a separate directive which says, please flush my cache. Please make sure that this variable is actually put out into the global shared memory so that whenever anybody else looks at it, they will get the right value. And so depending on the cache coherency hardware on your particular platform, you may need to use this. And so anyway, this is a lower level kind of thing. And critical sections, it just handles it all for you, and you don't have to worry about it. And here's yet another way to handle synchronization. It's called OpenMP single, and that guarantees that the next stretch of code will only be executed by one thread. So maybe this is where you're collecting all the partial results and putting them together. You really only want one processor to do that. And so if you say OpenMP single, one processor will execute it, everybody else will skip it. And the question is, who executes it? It could be whoever gets there first. That would be the single directive. Whoever gets there can do it first. And the other one is you say there's a master process where you've designated one process as being in charge of everything, and it will be the one that executes it. So all of these are variations that you can use. You may not need them all, but they're all there. So that's all we need to know about the syntax and the semantics. And so let's go look at an example and see how fast it runs. So we'll try parallelizing it in different ways and do some benchmarking. So this is going to be a very simple example that I've used before. So I have an array, a square array of numbers on my grid. And at each grid point, I'm going to average the nearest neighbors and update my value. So I'm going to loop over the x dimension, the y dimension, and independently do all that stuff. And I'm going to do that repeatedly a certain number of time steps. So we've seen this pattern before. So let's see how it looks in OpenMP. Somebody else animated this. Okay. So I'm going to have an OpenMP parallel for that says that all the for loops that follow can be run in parallel. And the grid is going to be shared by everybody, but the values of x and y are going to be private. So everybody gets to see the grid because everybody needs to know, look at the data because you have to know not just your data but your neighbor's data. But every process is going to have its own private values of x and y because everybody needs to know, where am I, and that's x and y. And then at the end of these for loops, after they've all finished executing, there's implicitly a barrier synchronization. You won't get past this closed bracket until all the processors have finished their work, and then you continue, right? So that makes it easier to program. And here, I'm now going to take that grid and swap it with another grid because I'm doing multiple time steps, and so I'm sort of ping-ponging back and forth between different time steps. So here's going to be my basic code, and what I want to do is try to parallelize it in several different ways. And then I'm going to put up some performance data as to how well it works. So I'm going to parallelize it 3 different ways using OpenMP, and then just for fun, I'll also parallelize it using Pthreads and compare the performance. So here is, and it's based on an ocean code, an ocean simulation code. So that's just sort of tells you what the nearest neighbors are. It's doing some sort of Navier-Stokes solve. And so what I'm going to do in this first code is I'm going to traverse the entire square ocean. And I'm going to do it row by row. And I'm going to assign row iterations to threads with dynamic scheduling. So here, imagine I have this 8 by 8 grid. And what I'm going to do is I'm going to take the first 8th of the rows and assign it to the red processor. And then the next 8th of the rows get to the blue, and then the purple, and then the green. And since I'm doing it dynamically, you don't know which subset of rows you're going to get. So the red processor is going to get the first chunk of rows and the 7th. Just because that's what the dynamic scheduler happens to do. So that's going to be my first implementation. So the next implementation is going to be static scheduling. I'm going to pre-assign one pth of the rows to each process. And so that's what it would look like here. If I have 4 processes, the first process will get the first quarter, the next process will get the next quarter of the rows, and so forth. So you would think these would have very similar performances, but what I'm going to be measuring here is there any overhead from doing it dynamically versus doing it statically? So we'll see if there's a performance difference. Now, when we did this example earlier in a previous lecture, we said you can certainly assign by rows, but there's other shapes that we could assign by. And if you want to minimize the amount of data that moves between the red processor and the blue processor, is this the right way to do the assignment? We said that the right way to decide what the red subset should be is you want to minimize the surface to volume ratio. You want to minimize the amount of edge crossings between the red and the blue because that's what represents communication. And so let's do squares. And so each thread is again going to execute a square-shaped region. So now the communication is determined by the perimeter of each square, and that's going to be less. So I suggested that was a better idea before. This is all shared memory, right? So maybe it shouldn't matter, but we'll see what happens because there is going to be some communication between one cache and another. And so those are the three OpenMP implementations I'm going to measure. And then I'm going to do it exactly the same square distribution, but I'm just going to do it with Pthreads. So it's going to be the same algorithm at a high level. It's just going to use Pthreads to do all the parallelization just to see if that makes a difference. Okay. And so that's going to be in OpenMP, and that's going to be in Pthreads. So I'm going to do two benchmarks, and one for a relatively large ocean and one for a small ocean. So for the large ocean, where there's a lot of work to do per processor, that should kind of make it less important which one of these I choose. I won't see the overhead of creating threads. And then I'll do it for a small ocean, and we'll see a difference. So here are speedups. And so here are the four different ways of implementing it. These three are OpenMP. This is Pthreads. This is speed up compared to one processor, so up is good. And I'm running it on 1, 2, 4, 8, and 16 processors. And it's all normalized to the speed on one processor, which is therefore at 1. And these are the OpenMP versions, and there's Pthreads. And if I look at the best case, which is squares, the speed goes from 1 to 2 to 4 to 8. That's kind of the perfect speed up I'd hope to get by going to doubling the number of processors at each example. But here, instead of 16-way speed up, I only get a little over 14. At this point, the overhead from communication or whatever is starting to hit, and I can't, I'm running out of parallelism. Pthreads does almost as well. OpenMP is doing a little bit better. But the squares definitely beat out the row allocation ones, which, you can do the comparison and see it's not quite as good. So what's the takeaway? Is that squares beat rows, and you get a perfect speed up to 8. OpenMP is a little better than Pthreads, and there's not much difference between dynamic and static. Now, if you wanted to be an expert programmer and hack the Pthreads code for a long time, you could make these equal, but the whole point is OpenMP is easier. That it's meant to be easier to program, and you don't have to spend a lot of time doing lots of clever, detailed programming. Okay, so that's the big ocean. Now let's go to a small ocean and see what the difference is. And so now, it's all normalized to speed up of 1. So why is this less than 1? So what do I mean by I'm comparing it to the speed on one processor? I take the sequential code, right? The common sequential code, and I say how fast am I compared to that? And this version is actually slower than the processor, than the pure sequential code. So it actually slows down a little bit. But then it speeds up more. I don't get anywhere nearly as good a speed up. This is only 8-fold speed up out of 16. And that's because there's not nearly as much work to do to assign to each processor. And it also, OpenMP is now beating the overhead from Pthreads. So why is it that OpenMP can beat Pthreads? I mean, they're running on the same machine. So it's because the overhead of doing all this thread allocation in the operating system is not done here. So OpenMP sort of pre-allocates a bunch of processes. You don't see that cost. And then at runtime, it takes these pre-existing threads and allocates them and gives them to you to do work. And if your problem is really small, you'll see that big difference. Okay, so let me just sort of summarize the takeaways from this. So OpenMP scales 16 processor systems. We got 14 out of 16. The overhead was too high, and when it was a small problem, but when it was big enough, it was okay. The compiler-generated code, that means the OpenMP code, was indeed at least as good as Pthreads, which is the handwritten stuff. In fact, sometimes it was a lot better. So how did the loop scheduling affect performance? The dynamic stuff helps when you have variable amounts of work assigned to each loop iteration, but that wasn't the case here. Every sub-chunk of work cost the same. Each row was as expensive as every other row. So here, static was just fine. So it's a good tool to parallelize at least some applications. And so, and there's lots of material online. I don't really want to say any more than this. So it's a compiler-based technique to create concurrent code for mostly sequential code. You basically just insert comments that say, please do this loop in parallel. And it's not a silver bullet if you have a much more irregular application. If you don't have if you're searching down a tree and you don't know what the search tree looks like until you get down to the bottom of it, and some leaves may be much more expensive than others, that's very hard to express as a loop or a nested loop, so it's not going to work so much there. But for many scientific applications, this is perfectly adequate. So that's all I wanted to say about shared memory programming. And as I said on homework 2, you'll get to do this. And there are questions. Good.
For big scientific applications where people are already putting a ton of time into getting the code kind of optimized, and there might be, people who choose Pthreads or OpenMP, do you know what the breakdown is for what people use?
So people who program on, let's say, I think the most common programming model on a machine like Hopper, which is a hierarchical machine, because you have 24-way parallelism shared memory on each node, and then you have thousands of those connected together. So what people often do who really want to get the highest performance is they'll write OpenMP code that runs on each 24-way node, and then they'll write MPI, distributed memory code, that's the next lecture, to communicate in between the different processes on the distributed memory.
The one node work, though, they don't use Pthreads mostly?
No, I think OpenMP dominates rather dramatically. Another question?
So in the previous plot for the smaller, so it seems like Pthread is doing well until 8 processor, and then suddenly cuts down. So
so why did it drop? The question is, why did it drop going from 8 to 16?
Until 8, seems like it's doing better than OpenMP.
So this to get a really good answer would require a future lecture which talks about the performance monitoring tools, which would automatically tell you where all the time goes, because it requires sort of going in and saying how much time was spent in the arithmetic, how much time was spent in the communication, and how much time was spent in the overhead of calling the tools that create it. And that's hard to reason about unless you have instrument your code, and people have built special tools to do that instrumentation. So what I believe is going on here is that the overhead of creating threads, when you went from 8 to 16, it just dominated the amount of work that you had to do. Right? It didn't pay off anymore because there's so little work to assign to each of these 8 to each of these 16 compared to each of those 8. When the problem was bigger, that didn't occur so much. Good. Any other questions? Okay. So, please.
So does that mean if the computing task is getting even larger, and the performance of Pthread should, have a close performance as OpenMP?
So the question, maybe I'll ask. Perhaps the question is, does Pthreads ever have an advantage over OpenMP? And I would say that if you have a very irregular application, then there are algorithms you can express by very detailed programming using Pthreads constructs, which gives you a lot of freedom to allocate processes and control everything about how much work is assigned to each one. That gives you much more freedom than OpenMP, where you were just parallelizing loops. And so for irregular applications, Pthreads gives you a lot more freedom, but OpenMP is much easier to use. So there's this trade-off between ease of use and expressiveness. And when we do the next lecture on distributed memory processing, you as the programmer will be much more responsible for doing all of the details about each assigning work to each processor. So you will not escape the need to do that. Okay, so let me now Okay, so now I'm going to go back up the stack from the programming model, how do you write parallel code in software, to a little bit about algorithms. And the cute name we give to this are tricks with trees. And the reason for this is that the next programming model I talk about, MPI, has built-in subroutines that implement a lot of these tricks with trees, because they're so common that they've decided to make them available, as standard MPI subroutine calls. And so in order to see why they would be in there at all, I need to tell you about these basic algorithms that involve trees. And so I'm going to start by telling you that any function that depends on n inputs and you want to evaluate it in parallel, you can't possibly do it faster than log n steps. So that's just sort of a general lower bound for any function that depends on n inputs. So the natural question is, what can I do that fast? And that's what MPI has a lot of built-in functions to do. So the simplest thing that you could imagine is, suppose you have n numbers and you want to add them all up and get the sum. That's called a reduction. Then the natural thing to do is add every pair of numbers, you get n over 2, then add every pair of those, you get n over 4, and after log n steps, you're done. That's an incredibly common thing to do. And equally common is a broadcast, where one processor has a number, you want all the processors to know it, and again, there's a tree. One processor tells 2, 2 tells 4, 4 tells 8. That's a natural thing to do in log n time. But there's a lot of other much more clever and surprising things you can do with trees. So the building block is not to just compute, let's talk about sums, the global sum of a bunch of numbers, but to compute what's called the prefix sum of all those numbers. That means I want to compute not just x1, but x1 plus x2, x1 plus x2 plus x3, x1 plus x2 plus x3 plus x4, all the leading sums, all the way up to the global sum, which is x1 through xn. Those are called prefixes, right? Because it's 1 through k, for all k from 1 to n. It turns out you can compute all of those in log n time, and very efficiently, using a tree. So it turns out that people have been using this algorithm since the dawn of computing. Every computer that's been built for decades uses this algorithm to add n-bit integers. And that's because it's not just summing that you do. You can do any associative operation and compute the prefixes. And by picking the right associative operation, you can add n-bit integers. And this is built into all hardware. I'll tell you about that. The same trick lets you multiply n by n matrices in log n time. The same trick lets you invert triangular matrices in log squared n time. That's not necessarily, the best algorithm, but the point is it's surprisingly these little building blocks will let you do that. And in fact, you can invert dense n by n matrices in log squared n time just using these building blocks, in theory. More than that, you can actually evaluate arbitrary expressions. What's, plus, minus, times, divide, parentheses, anything you can write down, as long as they're, n values, you can do that in log n time using these building blocks. And then general recurrences, where xi is some function of xi minus 1. So the point of all this is to say that you want to recognize there's a tree hiding in your algorithm and use these tools when they're available, even if it's not obvious in the first place. And I will claim that many of these are not obvious applications of a tree. So those are each of those is going to be one slide each, because they're all very simple once you get the idea. I'm also going to talk about 3 more higher level applications where these come up. One of them is two-dimensional parallel prefix, not just computing leading sums in one dimension. This was the bottleneck in an image segmentation problem that we worked on in the Par lab. And by using this same sort of tree structure, that got sped up rather dramatically. You can use it to do sparse matrix vector multiply. That's the fastest way to do it on some platforms. And in fact, in your browser, when you're doing page layout and parsing HTML to figure out where to put the pictures in your screen, that's another example of this where people speed it up. And each of these can be a long talk. Again, I'll just give a couple word summary. And let me just say it goes on. And things that I will not talk about are solving tridiagonal linear systems, traversing linked lists, computing minimal spanning trees, convex hulls. I mean, you have to get used to the idea that trees appear everywhere, but I'll just give you a few of them. So I'm going to start by talking about this log n lower bound to compute any function that depends on n inputs. And so here is the idea. It's very simple. I'm going to assume that all I'm allowed to do are binary operations, so that in one time step I can take 2 inputs and do something with them and compute an output, like add them or multiply them. So if I'm only allowed one time step, how many inputs can the answer depend on? I can obviously only do one operation that depends on 2 inputs. What if I have 2 time steps? What can I do? Well, the very last operation depends on 2 inputs, and those in turn can depend on 2 more, so I could depend on 4 inputs if I only have 2 time steps. And I think the induction is pretty clear. After k time steps, I could depend on no more than 2 to the k inputs. And so if I want to depend on n inputs, I need log n time steps. And a binary tree is kind of the obvious candidate that makes this happen. If I have n inputs, it'll be log n deep to get one answer, no matter what function I want to compute. So here's the simplest example where I want to compute a global sum. So I have my binary tree, and at the bottom I have listed A0 through A7. And at each node in the tree, I look at my left child, my right child, I sum them and pass it up to the top. And after, in this case, 3 steps, I get the global sum. So this is an obvious property of addition, but what is the only really mathematical property I need of that operator? I mean, if these were numbers, what else could I do for this and have this algorithm work besides addition? Multiplication would work fine. Taking the max or the min would work fine. So what's the only mathematical property of plus that I really depend on? Associativity. I can have any associative operator here. But there are a lot of associative operators in the world, right? I mean, these could be, for example, 2x2 matrices that I were multiplying. We'll see that example later. And it would still work, right? So I really don't need very much mathematical properties in order to use this. So, and the other thing, of course, you do with a tree is suppose one processor knows now the global sum. You want everybody to know it. So he wants to broadcast this global sum to everybody. You just go back down the tree, and it takes you log n levels. He will tell the 2 children, their children tell their children, and so forth. So now what I'd like to do is say, I want to compute not just this global sum, I want to compute every prefix sum. I want to compute A1 plus A2, A0 plus A1, A0 plus A1 plus A2, all 8 different possibilities. It turns out that all I have to do is run this algorithm twice. Once going up the tree and once going down the tree. So let me just show you the picture, and then I'll write the general code in the next slide. So here, this could be any associative operator, as I said, but plus is good enough for now. And here I have p numbers, and I want to compute all the leading sums. The sum of x0 through xj for all j's. So here's what it looks like. And what I've drawn here are 8 processors, and each level indicates what they compute at each step. So I start with where processor 0 owns A0, processor 1 owns A1, and so forth. And I've color-coded it by the final values that I actually want are in blue. Okay, so here initially everybody owns 1 value, then I run my binary tree, everybody computes the sum of 2, compute the sum of 2, compute the sum of 2, and I finally get the global sum sitting there. So that's the same thing I did before. And as you can see, I have some of the final answers. I have A0, I have the sum of A0 through A1, the sum of A0 through A3, and then the global sum. But I want everything else too. So now I'm going to go down the tree in the opposite direction. If I take A0 through A3 and add it to the sum of A4 plus A5, I get the sum of, I get the sum of 0 through 5 by taking that value and that value. That's the sort of the going down one level in the tree. And so now I take the sum of A0 through A1 and add it to A2. I get the sum of A0 through A2. I take that and that. I get the sum of A0 through A4. And I take that and that, and I get the sum of A0 through A6. And finally, I have all the leading partial sums. And I've gone through the tree twice. So that's the simplest example. But now let me just tell you what the code is. There's basically 3 lines of code that are executed at each vertex in the tree. Once going up and once going down. So let me just tell you what it is. So there's going to be an up the tree phase, going from the leaves to the root, and a down the tree phase. And here I've illustrated with an example. So what do you do? What does each node in the tree do on the way up? You get a value from your left child and your right child, and you add them, and you pass it up to your parent. But I'm going to do a little bit more. I'm going to save the value of my left child in a local register called lsave. So I'm keeping the value from my left child on the way up. And by induction, what is lsave? It's the sum of all the leaves in my left subtree, right? Because it's what my left child told me, so it's the sum of all my left subchild stuff, right? I keep that. So then I get up to the top and I have the global sum, and now I go back down again, and here's the algorithm. I'm going to take a number from my parent, the root gets 0, and I'm going to send that value to my left child. So I just take my parent's value, send it to my left child. Then I will take my parent's input, add it to lsave that I saved, and send that to my right child. And what the induction says is that what is S when you're in the middle of the tree? It's the sum of everybody to my left. So that's the prefix sum that I want. So just to do an example here. So I add up 3 plus, let me do this correctly here. So I add up 3 plus 1, and I get a 4, but I save 3. I add up 4 plus 2, and I get 6, but I save the 4. And finally, at the top, I add 6 plus 9, I get 15, but I save the 6. So that's the way up. On the way down, I get a 0. So here's 6. I pass 0 down to that child, and I pass 6 down here. So 6 is the sum of everybody over here. Then he gets a 5, so I add 5 plus 6, pass him down there. But 6 gets passed out there. That's the sum of all of that. And so I have enough information for all of the summation to my left. And the induction works, and that's how it does. So the only, if you like, disadvantage of this is that I'm doubling the work. I'm doing twice as many adds as I normally would, but I mean, who cares? I'm running in parallel, so it's just fine. So now, does everybody have any questions about that simple go up, go down algorithm, which is built into many systems, as I say? So let me just give you some examples of where it can be used in some surprising ways. So the first one is computing Fibonacci numbers, right? So I give you F0, I give you F1, and I just keep adding the last two numbers to get the next one. I want to express that as a prefix sum. Well, actually, not a sum, but a prefix associative operator. So how am I going to do that? Here's the trick. I'm going to take two consecutive Fibonacci numbers and stack them into a little vector. So there's Fn to Fn minus 1 to Fn, and I want to get the next pair. How do I do it? Well, it turns out that all I have to do is multiply these pairs by this 2x2 matrix to get the next one. This says sum Fn and Fn minus 1 to get Fn plus 1, and just copy Fn down there. So to get from this stage to that stage, I multiply by a little 2x2 matrix. So how do I get all of them? Well, I want to multiply by the 2x2 matrix once, twice, 3 times, 4 times to get all of them. So what I want to do is parallel prefix on this set of data. And so the inputs are 2x2 matrices, and the associative operator is 2x2 matrix multiply. So if I compute all the products of these guys up to that point, then that tells me how to get, F6, and that one tells me how to get, F8 or whatever. So it's just 2x2 matrix multiply as your associative operator. And this is kind of a prelude to what every piece of hardware does, has this built-in to add integers. It's 2x2 matrix multiply, except it's not integer matrix multiply, it's Boolean matrix multiply. So this is called carry look ahead. As I said, it's built into all hardware. I want to add two n-bit integers, and I want to do it in log n time. So how do I do that? So I have one integer a, and they're the bits. A0 through an minus 1 are the bits of a. b0 through bn minus 1 are the bits of b, and I want to get the sum, s. And so here's the elementary school algorithm. I'll just add the bits from left to right, from right to left, sorry. So, and at each step I have a carry bit, right, which says, do I have to carry a bit forward? So there's no carry at the beginning. And then going from right to left, I say, what's the next carry bit? And there'll be a carry bit if the sum of the bits is at least 2. And so here is some information that does that. I ask, what's the next carry bit? So I take the two current bits. I say, is at least one of them 1? And the carry input is 1. Or both the bits I'm adding up are 1. And then once I know the carry, I can tell you what the current sum value is. If I have I'm adding up now 3 bits, A, B, and my carry in. And if there's an odd number, then I get a 1. So AND is a Boolean operator. OR is a Boolean operator, and XOR, exclusive OR, is a Boolean operator. And it gives me a 1 if exactly one of those is 1. So I claim this recurrence, which goes from CI minus 1 to CI, is 2x2 matrix multiply, where it's a Boolean matrix multiply. So what am I going to do? I'm going to pre-compute in parallel all of these things here, AI, XOR, BI. Those are all independent, can do that in one step. Those are called propagate bits. And then I'm also going to compute all these AI and BIs, all in parallel. Those are called generate bits. That all happens in one step with a bunch of gates. And so how do I get to CI? I take PI and CI minus 1. I'm just copying this line of algebra down here, or GI. And then I'll just do this trick by having a 1 bit at the bottom. So then I recognize that this is really just a 2x2 matrix multiply. And what do I mean by matrix multiply? Multiply is and addition is OR. and all the rules of associativity and distributivity, they all work for Boolean algebra just like they do for regular arithmetic. So this says pi and ci minus 1 or gi, and then the 1 just gets copied. So I'm just multiplying by all these 2 by 2 matrices. And the same trick that I did before, it's parallel prefix, and with this particular operation, and it all runs in log n time. Okay. So let me just say that there are a lot of other applications of this parallel prefix operation. And scan is, since it's been invented many times, people make up different names. So scan is just a synonym for parallel prefix. So I could add multi-precision numbers in just the same way, where I have a long array. I can evaluate recurrences and expressions, solve tridiagonal systems, all of these different ones. I'll just do a few examples. And it has different names in languages that go back decades, like APL. It's called +/. It's called cum sum in MATLAB. And the subroutine in MPI, which I'll talk about next time, is called MPI scan. And the only drawback, if you like, is that if I did it sequentially, I'd only need to do n-1 of those associative operations. Now I'm going to do 2n. But since I'm doing them in parallel, I don't care so much. So let me just do a bunch of examples of, I think, sort of surprising algorithms that reduce to this. So some of the examples are just going to be, gee whiz, I didn't know you could do that. But they're not necessarily practical. And some of them are, as I say, are very practical and important. So let me do some really simple ones. I want to multiply n by n matrices, and I want to do it in log n time. I don't need parallel prefix for that. This is just reduction trees. So what I want to do is I need to compute all of these products, aik times bkj, and add them up. So the first thing I do in one step with n-cube processors is I compute all the n-cube products that I need. And then I got to sum all these guys, for k equals 1 to n in order to get the sum. And so I do that with n-squared trees, each one of which has, n vertices in it, and I can compute all those sums. So that's sort of an obvious thing to do. If I had enough processes, I could multiply n by n matrices in log n time. But what I want to do is invert n by n matrices almost that fast. So this is going to be a building block. So the next step on the way to inversion of general matrices is I'm going to invert triangular matrices in log squared n time. So here's the trick. Here's my triangular matrix. It's n by n. Let me break it up into subproblems. So I'm going to write down something recursive. And it's a little fact from algebra that you can check that if I invert this triangular matrix, I get this triangular matrix. And A turns into A inverse. So there's a problem of half the size. B turns into B inverse. And to get that corner is matrix multiply by the other corners. So here's my nice simple divide and conquer algorithm that runs in principle in log squared n time. I'm going to do divide and conquer. If my original matrix is 1 by 1, then I just do the division and return the answer. Otherwise, I break it up into these problems of half the size. In parallel, I invert A and I invert B. So I call the same subroutine in those two corners, and that runs in parallel. And once I get those answers, I do those matrix multiplies. And that fills in that corner, and I return the answer. So the question is, how fast does this run? So I'm going to write down a recurrence. The time to call this triangular inversion routine in an n by n matrix. Well, first I have to do these two n over 2 problems, but they run in parallel, so that's the time of an n over 2 problem. Sorry. And then I do matrix multiply, that's log n, and if you solve this recurrence, you get log squared n. So that's a building block. And now I want to do general dense n by n matrix inversion, just as fast. And I'm just going to sort of sketch how that works. It involves a few theorems by some famous people. So it turns out that, and I hope you remember this from your linear algebra class, you can write down A inverse as a polynomial in A. So you can write down a formula that says A inverse is something times A plus something times A squared plus something times A cubed. And so if I had those coefficients of that polynomial, then I could just evaluate it, and that would give me A inverse. That polynomial has a special name. It's called the characteristic polynomial. Okay, so the question is, how do I get the coefficients? And another famous person wrote down a theorem that said, if I want the coefficients of that polynomial, they're the solutions of a triangular system of equations. I know how to do that. So all I need to do is write down that triangular system and solve it. So what are the entries of that triangular system? That's a little bit of work. There are these numbers called S. And where do the S's come from? They come from the traces, the sums of the diagonal entries of the powers of the matrix. So if I had all these powers of this matrix, of the matrix, and sum their diagonals, I'd write down this triangular system and I'd solve it. So here's the algorithm that was first written down in 1976. I'm going to compute all the powers of this matrix, a squared, a cubed. That's parallel prefix. What's my associative operator? It's n by n matrix multiply. So that costs me log n, and since it's parallel prefix, it's log n times log n, or log squared n, to get all of these powers. Then I just sum all their diagonals. That's a bunch of independent reductions. I can do that in log n time to get all of these s's. Then I fill them in this matrix, and I have a triangular solve, and that costs me log squared n using the algorithm in the previous slide. And then I just evaluate this polynomial, and that's another bunch of reductions, and log n altogether. So this, was surprised everybody that you could do it this fast. And it only has one drawback. It's completely numerically unstable. It gives you complete garbage as an answer. So in fact, if you were to take a 20 by 20 matrix, the identity matrix times 2, so just 2's down the diagonal. We can all invert that one in our heads, right? And I apply this algorithm, I get noise. Complete noise is the output. And that's because of floating point stuff. So this might be interesting over a finite field, but it's certainly not interesting when you have round off. But these algorithms do exist, right? So you have to have a little more, you have to know more than just the algorithm exists. Sometimes you need some expertise as to whether it's a good idea or not. But it's interesting that it exists. So that's all I wanted to say about that dense linear algebra. But what's maybe even more surprising is I can evaluate arbitrary expressions in log n time. What do I mean by an arbitrary expression? That means write down whatever you want. There are n input values, and I can add them, subtract them, multiply them, divide them in any order with parentheses. So I get this kind of arbitrary binary tree with n leaves that I want to evaluate. And a long time ago, someone named Brent proved that you could cleverly reorganize that in order to do it in log n time, where you're allowed to use commutativity, associativity, and distributivity to sort of reorganize all that stuff. So he had a very clever, complicated proof at the beginning, but there's a modern proof, and it just uses parallel prefix. And here's the idea. I'm going to take that expression tree and just evaluate it greedily. So that means I'm going to start by looking at all the leaves, which are at the bottom. There's no dependencies. I just evaluate it, right? So if I have a plus b at the bottom, I evaluate it. And then I look at the tree that's left over, and I ask, are there any long chains where I have just sort of linear sort of a straight line up the tree. And then I evaluate that with parallel prefix. Then I go back and I collapse the leaves. And then I go collapse the chains. I just keep doing that greedily as I go up, and the whole thing magically turns into log n. And you're not going to do it faster than log n, as I said. So that's a surprise that you can do. And let me just do one more example, which is evaluating recurrences. So this is my last sort of gee whiz example before I go on to the practical ones. So what I want to do is I'm given a value x sub 0 and some rational function fi, and I want to compute x1, x2, x3 by repeatedly evaluating this rational function. And the question is, how fast can I get to x sub n? So I'm given all the functions, and I'm giving x0. So here's the theorem. Let's suppose that all of these functions have the same degree. So they're all linear functions, so it's linear divided by linear, rational function, or quadratic divided by quadratic, or cubic divided by cubic. So d is the degree. Then if they're linear, so it's a linear divided by linear, I can do it in log n time, and it's parallel prefix. And that's as fast as you can go. But if the degree is bigger than 1, you can't do it faster than sequential. Sequential wins. It takes you, order n time to get x sub n. And so there's a big gap there. And so here's the proof. It just turns into 2 by 2 matrix multiply again. So suppose I want to go from xi minus 1 to xi. And fi is a linear rational function. That means it's something linear divided by something linear. Then what I'm going to do? I'm just going to compute the numerator and denominator separately, and I'll divide them at the end. So here's my numerator and denominator, and each one is linear, right? So all I need to do is take linear combinations of the previous numerator and denominator and these linear combinations, and it's 2 by 2 matrix multiply. I'm calling this little 2 by 2 matrix m sub I. And that just propagates, and it's 2 by 2 matrix multiply, and it's parallel prefix. And so you can do that. Now, why can't you possibly do it faster than sequentially if it's bigger? And the reason is that if I think of this function as a rational function of my inputs, what's its degree? So if it's linear, everything is linear, right? So the last guy is some rational linear function of the inputs. But if it's quadratic, after one step I get the quadratic function. Then I get a quartic function. Then I get a degree 8. Then I get degree 16. It grows exponentially. And so after k parallel steps, I'm going to have something of degree d to the I, where d is the degree. But if you also ask how fast, if I do any work at all in k parallel steps, if all I'm allowed to do is multiplies and divides and adds and subtracts, I can't do more than double the degree every time I do an operation. So if I want to have a degree of 2 to the k, I have to have a chain of k operations. So I can't do any faster than linear. Okay, so that's the last sort of gee-whiz example. And I will now stop here and say the next real example where this is used in practice is image segmentation. And so now we're going to do parallel prefix again in order to decide where's the panda and where's not the panda, except it's going to be two-dimensional parallel prefix instead of just along one degree. So I'll finish this next time. Are there any questions? Okay, so anything more about homework? So you should have gotten an email from about assigning teams. So if there's any questions about your team members, like perhaps they, dropped the course and didn't tell you or something, we can talk about it. Okay.